Oh. The question I always had, oh, that didn't line up very nicely, did it? Oh, well, tough luck. Needs a little fixing. So, the Earth's past has been very troubled. In the past, the Earth has gone through all kinds of horrific, violent episodes. And I'm not going to talk too much about that. I mean, there was a time where the Earth was inundated by a very strong solar wind that blew our atmosphere away. Maybe that's what's being indicated here, kind of a solar wind coming in and blowing our atmosphere away. So there's been various times where life has had to reassert itself. And in fact, there was a recent paper that came out from a Harvard astronomer that said that there is every reason to believe that at some point in the Earth's past, there could have been a civilization with intelligent beings. It seems a little far-fetched, but on the other hand, interesting to think about. So first, a few pictures. This is from Kira, Boulder, Colorado. These are the Flatirons over here. The reason I know this is that I went to graduate school in Boulder. I did a master's degree in, it's crazy stuff. Anyway, ancient history. And Boulder's a beautiful town. It's just on the east side of the Rocky Mountains, right there in the foothills. And this is a beautiful image of snowfall in that area from Kira. Nice sunset from Krista May. Charlene sent this. Pretty fascinating. You got high clouds or mid-level clouds up here that are well above the mountains, and then coming across the mountains, this is the Waianae Range. You've got this crazy looking, looks like a monster that's starting to envelop. There's been some strange clouds. In fact, Diamond Head had a shroud of foggy cloud just capping the mountain the other day, and I didn't stop and take a picture of it. It was really interesting. Our weather, the rainy weather also brings the opportunity for some great rainbows, and this is from Zixin. Fabulous photo taken from Magic Island, I suspect. Nice double rainbow, thank you for that. Last time we talked about air pollution, and oh, interesting. And what were the subjects? Had a bit of history, talked about horses, planetary boundary layer, that's the lowest part of the atmosphere that's capped by in our case, the trade wind inversion. That's where the pollution goes. The conditions that promote air pollution episodes, that would be high pressure and a stable layer, like a boundary layer cap that prevents vertical mixing. And then we talked about acid rain. The causes of acid rain are sulfur dioxide pollution and nitrous oxide pollution. The former sulfur dioxide pollution comes primarily from coal-fired power plants and Kilauea, and the nitrous oxide come from vehicular emissions, so cars and trucks. And then VOG, we talked a little about VOG, which is primarily a sulfur dioxide problem. So you get sulfuric acid and acid rain from our happy volcano. All right, so what about our past climate? So today we're going to talk about the past climate, going back in time. What do we know and how do we know it? So first I want to define what we mean by climate, because it seems like it's not all that clear to many people, what do we mean by climate? Some people like to say that climate is the personality of the atmosphere, and weather is the mood of the atmosphere. So that's sort of an idea. So then we're going to talk about what controls climate, and then past climate. And then we're going to talk about recent warming. What do the data show about warming? And we're not going to go too deep into that. Just basically look at the atmosphere and the ocean and how it's been warming in recent decades. So what is climate? Climate is the sum of all weather events. And we're not just talking the average of the data. It's the average, sure, but it's also the extremes. Like if we're thinking about local climate, we might wonder what's the warmest it's ever been in Honolulu, and the warmest high temperature, and what's the coldest low temperature that we've ever seen. And I think in Hawaii, that's 95 is the hottest it's ever been, and 53 degrees Fahrenheit is the coldest it's ever been. So that's basically the range of our climate here. But it's also the means and the extremes. So coastal lows, how often do you have a coastal low? Or how often do you have a hurricane? All those factors belong to climate. And in fact, when they do climate modeling, they want to have enough resolution that they get the hurricanes. Because hurricanes play a huge role in the energetics of the Earth's ocean system. So they want to get that information. Okay, so what controls climate? Climate of the Earth as a whole is controlled by the balance of the incoming solar radiation and the outgoing infrared radiation. We talked about this when we talked about radiation. So the radiation balance is a little subtle in that the outgoing radiation from the Earth is emitted from every surface of the sphere, whereas the incoming radiation is intercepted only by the disk of the Earth. So there's a factor of 4 difference in terms of the geometry. Something to think about. Anyway, but if we didn't have an atmosphere, we'd be down at minus 18 degrees C. And there were times when we didn't have an atmosphere. And it would have been interesting to see, what the Earth's climate would have been without an atmosphere in the distant past. Of course, the Earth might have been hotter in terms of geothermal activity. A lot of outgassing, that's where we got our atmosphere after it was stripped away by the sun. Okay, so back to, climate change as we've been able to ascertain it from data. There are, talking about this radiation balance now, just the incoming radiation versus the outgoing infrared radiation, there are 2 sides to it. The external forcing affects the solar radiation coming from the outside, okay? So things like astronomical impacts, if the sun changes in its output, then that would be an external change to the climate. If the Earth's orbit or the tilt of the Earth's axis changes, that would be an external change because it affects the sunlight. If we run through a big interplanetary dust cloud, that would reduce the amount of solar radiation. And what if we had a collision with an asteroid? So these are all the external forcings. And then what about internal forcings? These are forcings that have to do with sort of geoscience, the Earth and the atmosphere. Atmospheric composition is at the top here. That would be the greenhouse gases and how many there are and how warm they keep us. Surface characteristics, how much of the solar radiation is reflected back to space because of ice and snow, or changes in the surface due to urbanization, for example. That's sort of what's indicated here in the lower right. Ocean currents, changes in ocean currents can be important. Volcanic activity, because it's spewing a lot of particulate matter into the atmosphere and blocking the sun. But again, it's an internal thing because it's part of the Earth. And then finally, continental drift. And there may be others that aren't listed here, but gives you an idea. It's external forcing versus internal forcing. So here is an animation of the known asteroids near Earth. Earth in this is, I think this white line is Earth. Mercury, Venus, Earth, and then Mars. So Earth, this white line, as you can see, there's a ton of stuff out there. And right now there is a very large telescope called Pan-STARRS, located at Haleakala, where they are looking for asteroids. And it's a project that's funded by NASA, I believe. And if they find one that's actually looks like it's going to strike Earth, they're going to try to do something about it. They'll send up a rocket. Hopefully it won't blow up on the launch pad. There's an interesting movie, I can't remember the name of it, that shows an asteroid coming towards Earth, and the politicians are arguing about whether they should, do something or not. And in the end, there's just this, they don't want to deal with it because it's politically unpopular to talk about negative things. So they don't do anything, and the whole Earth blows up at the end of the movie. It's a recent movie. What's its name? Don't Look Up. Yeah, Don't Look Up. If you haven't seen it, it's kind of a comedy. It's pretty funny. Leonardo DiCaprio stars with Jennifer Lawrence. Yeah. So anyway, the reason that's topical is because climate change is a bit like that, right? Are we going to do something about climate change or not? Okay. So going back in time, here's a graph that takes us way back. This is millions of years before present, so this is 500 million years at the beginning here. And this, the farther back you go in time, the less we know. Our current climate is right here, and this is not a linear curve. So at the beginning here, this is in thousands of years, and then it goes into hundreds of thousands of years, and then it goes into millions of years. So it's not linear. But you can see that, the climate's been pretty stable back to the last ice age, and then there's an ice age here, 20,000 years ago, there's a peak ice age. And then it changes, the scale changes. There's a bunch of ice ages in here and some warm periods in between. We're in a warm period. And then before that, lots and lots of periods where the temperature of the Earth was warmer than currently. So I guess that the takeaway is that the Earth, over a lot of its history that we can discern, was warmer than now. That's the hothouse part here. And then recently, it's been colder than average. Colder than now, anyway. Okay. And then the question is, what's going to happen in the future? So, dinosaur period, a lot of that, it was quite a bit hotter. So I'm not going to read this. It's here to give you a little bit of a sense of how it is that we look at the past. I kind of like doing it in pictorial form. There's lots of ways. We have boreholes that go down into the ice, and we look at ice cores. That's a very important source. Another interesting source is looking at the history of tree rings. We have trees that are thousands of years old in the United States, the white pines. And we can look at, just do a very, very narrow, take a very narrow plug of wood out from the center of these trees so that we don't hurt them. And we get the history of the climate going back thousands of years in the American Southwest. You can look at pollen that is fossilized, also insects that are fossilized. You can look at lake levels, sea levels, glaciation. So there's lots of different ways to look at the past climate. And they're all independent. There are, different people do different kinds of science when it comes to our paleoclimate, climate past. Another slide talking about what you can do with trees. This is called dendrochronology, and it sort of explains what these tree rings mean. If you go on a hike, you sometimes see a big tree that's fallen over the trail, and they've sort of taken a piece out of it so that you can walk by. It's interesting to look at these tree rings and to see what was the history of life for that particular tree. And you can see it year by year. When you have a thick ring like here, that is white, that's a really good growing season during the summer, probably lots of rainfall, and it was, and sunshine. So it was really good growing conditions. And then the dark lines are from the fall, when the tree starts slowing down, but still growing. And so it demarcates every year, and you can count them. And this particular tree on the right goes, was born in 1527. That's a long time ago. It's fascinating to me that trees can be so old, that you can have a tree that was alive 2,000 years ago, at the time of Christ. It's interesting to think about. And these trees, it seems that they are sentient in ways that we're just learning about. They are able to communicate with each other about threats like insect infestations. One tree will tell another tree that, hey, I've got this bug over here, you better put out your defense system. And they can track that, and they can look at how the tree is responding. So it's very, very interesting. Trees are amazing. So one of the best ways we have going back, say, 800,000 years, which is almost 1 million years, is to look at ice cores. And the reason the ice cores are so good is that you can look at the temperature that's indicated from the ratio of the heavy oxygen to the lighter oxygen. Oxygen 16 is a normal oxygen. Oxygen 18 comes from cosmic rays that insert an added neutron, which makes it heavier. So the 18 count is how big the nucleus is. Anyway, that ratio allows you to say something about the temperature, because the heavy water is more resistant to evaporation. So during warmer climates, you get more O18, and colder climates, you get less O18. So there's two other things that you get from ice cores. One is you see the dust, how much dust there is. And the other thing you see is there are inclusions or bubbles of trapped gas. And they can sample the gas inside those bubbles and know what kind of gas, how much carbon dioxide there was in the atmosphere at the time. So it's pretty amazing. And here is some data going back 400,000 years from ice cores from Vostok and Antarctica. And you can see here the temperature going up and down, which is basically the oxygen isotope ratio going up and down. And then the carbon dioxide you get from the bubbles, and you can see there's a correlation. Temperature goes up, the carbon dioxide goes up. That does not mean that the carbon dioxide was driving the temperature. But it means that warmer climates, you tend to have more carbon dioxide in the atmosphere naturally through outgassing from the ocean. And then at the bottom here is dust. And you can see when the temperature is low, you tend to get more dust. Well, when the temperature is low, you're in an ice age. It's drier, there's less precipitation, and there's more dust flying around. So that all makes sense. But it's fascinating that these graphics, these graphs, they correlate so well. Here's temperature again with carbon dioxide and methane, all three tracking together. Now, if you go as far back as you can, it turns out you can go all the way back 800,000 years. This graphic only shows 400,000 years. And it shows our current climate, which is here. And you can see other warm periods with a lot of cold periods in between. So there's a lot of ice ages in here, mostly ice ages and a few warm periods. Sort of interesting. Now, why does this pattern look the way it does? And it turns out there's a correlation between the last graphic and orbital changes in the Earth, the way that it orbits around the sun and the tilt of the Earth's axis. Those are two things. And cool periods are associated with a more circular orbit and a smaller tilt in the Earth's axis. If you don't tilt the Earth's axis very much, you don't get much sunlight on the North Pole in the summertime or in the South Pole in the summertime. If you tilt the axis more, you get more solar radiation at high elevation angle during the summertime, and that creates more melting. And so that's sort of that is the explanation. So the tilt of the Earth's axis, defines the height of the polar midnight sun in the summer. More tilt equals more summer snow ice melt. I think that makes sense. If you have no tilt whatsoever, the sun just isn't going to provide any energy to the North Pole, and you're just going to allow the glaciers to form. So here's a graphic that has way too much data on it. The top one is the insolation at 65 degrees north. That's from the Earth's orbital mechanics. Okay, that's the top one. The surface temperature, it correlates, as you can see, all these kind of a little hard to see, but you can see the areas where it's highlighted with this, I guess it's a brown color. All these peaks are correlating with the temperature. They're correlating with the sea level. They correlate with the carbon dioxide, methane, the heavy oxygen, deuterium is heavy oxygen, and the ratio of the oxygen. So they all correlate to this orbital mechanics. So that's kind of interesting. Here we see it again. This is just the solar radiation at 65 degrees north in the red, and it shows in the green. It shows the obliquity contribution. That's how when it is that the Earth's orbit is seeing the eccentricity, how the eccentricity of the Earth's orbit interacts with solar radiation. All right. There's a point here that this is showing past and future, because we can predict this with models. And it's showing that in the near future, there's no cooling. So there's not much help from orbital mechanics to make us cooler. Now, the last ice age allowed migration. And it turns out that the most recent North American glaciers were at a maximum around 18 to 25,000 years ago. And sea level was 125 meters lower. That is, well, multiplied by 3, that's 375 feet, or 4, probably a little more, about 400 feet lower. And if it turns out that in Hawaii, there are beaches, evidence of coral and beaches 400 feet down if you dive, if you're a diver. And they've looked at this. The sea level has really changed a lot in Hawaii over time. So the thought is that there's this land bridge that developed, and it was kind of a dry area in here, and that's where Native Americans came through from Asia. The Clovis culture, they made really beautiful arrowheads, which survive nicely. I was going to put a picture of one in here. They date from around 12,000 years ago, and for a long time they thought that was about the time that humans arrived, and then it was pushed back to maybe 18,000 years ago, and most recently in the news they found these tracks in New Mexico, and they dated these tracks to 23,000 years ago. Well, that still fits with the Ice Age. 23,000 years ago, we were in the midst of an Ice Age, so that fits. But it's interesting, I guess people have been around for longer than and who knows, they might push that back even further. Because, I mean, it is possible to go from Asia along the coast in a boat, or you can come, there's many ways to get here. Maybe the Hawaiians made it, right? To go to Easter Island, and then on, the Polynesians went to, so that's all a little bit outside of the scope of the class. So let me get back to climate. There are some feedback mechanisms. And what is a feedback mechanism? It's, well, for example, when the ice starts melting at high latitudes, more solar radiation is available because it doesn't get reflected back to space. The albedo changes, and that is a positive feedback loop. So the ice melting creates more open water. The water is much better at absorbing the solar radiation, and you get warming. That's one of the reasons why high altitudes are warming faster than lower altitudes, because of this feedback mechanism. Another feedback mechanism is that if you add carbon dioxide into the atmosphere, you get an increased greenhouse effect. So you get more evaporation from the ocean surface, and that produces an enhancement to the greenhouse effect through water vapor. So water vapor goes in and out of the atmosphere rather quickly. It's not a climate change generator, but it is a slave to the CO2. If CO2 comes in, you get warmer planet, you get more water vapor in the atmosphere. It's a positive feedback. It's also possible to have a negative feedback loop. One of those is if you have a reduction in the ocean current because you have less cold water sinking that is driving this whole circulation. And that seems to be happening now. We have, and what does that do? Well, if you have less Gulf Stream, the northern hemisphere, Europe, is going to cool off. So that's a negative feedback loop because the Gulf Stream is getting weaker because of the increased meltwater on the ocean, and it short circuits the sinking motion of salt water, and therefore it weakens this whole deep water ocean circulation. And that then results in a weaker Gulf Stream and colder conditions in Europe. So this is a graphic showing temperature going back in time. You can see that there was a very cold period here. This is about 18,000 years ago, but even at 20,000 years ago, it was very cold. And then there was a little warming, and then it cooled off again, and then this is something called the Younger Dryas at 11,500 years ago. So the question is, why did this happen? Why was there a sudden cooling of the climate? It looked like we were coming out of an ice age. We got almost as warm as the present climate, and then we dropped back, and we were back in the ice age. One negative feedback mechanism, which is related to the Gulf Stream, is that this big lake in Canada, which was created because of a glacier ice dam, suddenly burst because it was getting warm. So here it was getting warm, right? So the ice is melting, it's getting warm, and then the dam that's holding back this lake breaks and suddenly pours all this water through the Great Lakes and out the St. Lawrence Seaway and into the North Atlantic, and that causes the Gulf Stream to be short-circuited, and then it pushes in a negative feedback way, pushes us back into an ice age in the Northern Hemisphere. There is an alternative theory for that, and this new theory says there was an asteroid or a comet maybe made out of snow and ice, something that doesn't leave much of a trace, and it hit in various places in the Northern Hemisphere, struck the Earth at 12,850 years ago, causing the cooling because it produced all kinds of stuff in the atmosphere. It blew stuff into the atmosphere, which caused cooling. So that's another. So there was a lot of things that happened at that time. There's impact debris found in North America and in Europe. That's what all these dots are. And a crater was discovered under Greenland ice sheet. There are mats of organic rich soil associated with wildfires. There was an extinction of megafauna, which of course can be due to humans too. And it was a human population decline. So, interesting. So this is the 1,000-year record. This is kind of a famous curve. They call it the hockey stick with recent climate showing warming. Now, what about volcanic impacts on recent climate? It turns out that when you have a big volcano that erupts, and we haven't had, historically speaking, or I should say geologically speaking, there were some immense volcanic eruptions in the distant past that could have created like a nuclear winter. A lot of stuff going up in the atmosphere. This is another picture of Pinatubo. I guess that's Pinatubo too. And this is what happens. Pinatubo happened, and then the global temperature dropped, or I should say the transmission of the atmosphere for sunlight dropped. This is the sunlight at Mauna Loa, so that's an important time series from Mauna Loa. This is Agung, which is Indonesia, which happened in a little earlier. And this is what Pinatubo did. It created this ash cloud that went all the way around the Earth, and it created that decrease in the global temperature, which is shown in this graphic at the bottom right. It's about a 2-degree decrease in temperature. So, and this is some past big volcanoes. Krakatoa is here about 1880. And Krakatoa was huge. 1815. So that's at a time when we have a lot of history from 1815. And it turns out that France was super cold. There were lots of thermometers in France at the time. So we knew that Europe was very cold. And it created all kinds of problems. It also caused Mary Shelley to write Frankenstein because she was so depressed by the weather. So she penned this very dark tale. You can see the price of all these foodstuffs are skyrocketing. So it's very bad for the politics. And then this picture on the lower right here, the bicycle was invented. And the reason that the bicycle, they think the reason that it was invented at this time is that there wasn't enough food for all the horses, and people were normally used to riding horses. And somebody with a little, I don't know who invented the bicycle, but I like bicycles a lot. I'm originally from the Netherlands. I was 3 years old when I moved away. So you think, well, how can I still be so Dutch? Well, my parents were Dutch, so they brainwashed me to believe that bicycles are the answer. And they gave me bicycles as Christmas presents and birthday presents. I had bicycles coming out. Anyway, bicycles are actually a very good way to avoid creating greenhouse gases. And I like them. That's when the bicycles were invented. Let's see, I guess that the point of this was it was another huge volcanic eruption in Iceland back in the 500s. So we're going back in time. And it seemed to usher in a more rapid decline for the Roman Empire, history seems to show. Okay, so this is the last little bit I'm going to talk about today. Just the recent warming, okay, the recent warming. And then next time I'll talk a little bit more about this. With sea level rise, just with a few more years, this guy is going to be toast because these guys are going to be able to swim over and just eat him. So there is a positive side of global warming for sharks. I wanted to put out a little advertisement. The dean of SOAS, interim Dean Fletcher, or I should say Chip Fletcher, is teaching this course. It's Earth 420. Now that number 420 may seem a little daunting, but it turns out it's a 101 level course. It doesn't have any math in it. It's rather simple. If you're at all interested in climate change, this is one of the best classes out there. And I understand that Chip's a good teacher. Yeah. You have to shout because I can't hear you. He gives it that number. He has that power as the dean. And you ask, why does he do that? Well, he told me, he gave me the answer to this. He says, by doing this, I tend to get students who are more interested in taking the class. I mean, and that way I don't know, people show up and it just works better. But I want you to know that it's all a ruse and you ought to take it because it's really going to be a fun class. Okay, moving on. So the Earth surface is warmed by greenhouse gases. We talked about that in radiation lecture, right? So if you amplify the amount of greenhouse gases in the atmosphere, it's going to increase the amount of infrared radiation that is trapped by those greenhouse gases and re-radiated back to the surface, okay? So this gets bigger and the surface gets warmer. So that's pretty simple. And you might ask, well, you know, the atmosphere is so huge. How can a few little parts per million of carbon dioxide make a difference? Well, it turns out the atmosphere is not all that huge. It's pretty thin and it's somewhat fragile. Okay, so who was the first person to kind of talk about this and to scientifically study the greenhouse effect? And I think it's interesting to note that it was a woman, and women are often suppressed in science. Back in the day, were in the past. I think that's not true now. But she was quite brilliant. And what she did was she had these glass enclosures that she would fill with gases, and she'd be able to measure the temperature as she, you know, beamed them with infrared radiation. And so she could see what the influence was of various gases. And that's how she studied it. It was not simple, but profoundly insightful. And that is the first person who did that. She was also a women's rights campaigner. Not surprising. Okay. And then there's a couple of these old white guys who also talked about global warming. This is kind of an insightful slide in that not all gases and particles are created equal. We talk about methane and nitrous oxide as also being greenhouse gases. But why is it that carbon dioxide is the one that is making all the news and the one that we are trying to control more than any others? And it turns out that if you put it in the atmosphere, a lot of it, relatively speaking, it stays in the atmosphere for centuries. And I mentioned just previously that water vapor does not. Water vapor cycles in and out in days or weeks. It comes up, it condenses out, it rains. Carbon dioxide doesn't do that. It sits in the atmosphere for a very, very long time. So that's the problem. We have to find a way to suck some of this carbon dioxide out of the atmosphere. I'll talk about that couple lectures in the future. So this is a large amount and it stays in the atmosphere a long time. So that's why it's considered important. Methane doesn't stay nearly as long, and nitrous oxides aren't really emitted to that same degree as carbon dioxide. So also not as important. Black carbon is here because this is the soot that comes out of coal-fired power plants, and it does block the solar radiation, so it causes some cooling. But again, it doesn't stay in the atmosphere for very long. So as soon as we get rid of all these coal-fired power plants, it's going to amplify the global warming. So that's the argument that coal people can make. It says, well, we need the coal because it's dirty, and therefore it'll hamper global warming. But anyway, the problem is it's also carcinogenic and it kills people. So it's not really a solution. So that's that. So now let's look at some data. I thought this was a funny meme or funny photo. This was a particularly hot day, and he was like, I can't take it anymore, hitting himself with some water. And you know, water, as long as the dew point temperature is low enough, you get evaporative cooling and it works well. All right. So what did the observations say about global warming? That's what I want to talk about now. And I've got this link here, www.climate.gov, or just climate.gov. And that's a site that is hosted by NOAA. Trump shut it down for a while, and now it's open again. It's very good. It has lots and lots of data, and it has the latest data. So you can go there and sort of say, okay, well, how much warming is happening? They are claiming that this is the warmest, it will be the warmest year on record. There's no question. 2023, in part because we have an El Nino. So we have a lot of warm water of spreading over a very large extent in the ocean that helps to warm the air right above the water, and therefore it helps to motivate this new record in temperature. So how do we measure the recent warming? Well, there's different ways to do it. One of the ways is looking at thermometers. The problem with thermometers is that they don't go back very far in time. You can see that the United States actually had very good coverage, probably better than any other part of the planet. Europe, not too bad. But much of the rest of the earth, there are no records, and they don't go back very far. So thermometers are limited. We have lots of modern observations. Satellites are the most important. Satellites are recent, though. Only since about 1970 do we have satellites, and really since 1980 are the satellites really any good for measuring global warming. But they're excellent. And the other thing we have is this Mauna Loa time series showing the carbon dioxide from the 1950s, mid-1950s. I think it was the IGY, the International Geophysical Year, back in '56 when they put it up there. And we've had record of CO2 ever since. CO2, of course, is consumed by plants. And so here you can see the northern hemisphere biological activity indicated by CO2. So in the summertime, there's less CO2. In the wintertime, there's more CO2. And that's what you have in this last diagram. This, as you can see, you know, it ramps up in the summertime, and in part because of there's more land area, land mass in the northern hemisphere, so we have more plants in the northern hemisphere. Evidently, that's why you get this nice curve. It has to do with the biology, and it goes to show the importance of the biology also in understanding climate. So if we plot the temperature, and this is ending in 2016 or 2017, so it's not completely current, and we plot over it the carbon dioxide, you can kind of see the relationship, that there is a relationship between the two. And the carbon dioxide is primarily coming from burning of fossil fuels. This is a carbon dioxide, I can't remember, okay, this is 2006, so it's not so current, but you can see there's a lot of carbon dioxide coming out of China. India doesn't show up that much. It would if you had a 2023 loop like this. You can see New York, you can see LA, you can see Europe providing some pollution. And of course, it's all blown around by the atmosphere, by the winds and the circulation in the atmosphere. There's also biomass burning. We have a lot of that in Africa, especially. So how do we know that the rise in CO2 is due to the burning of fossil fuels? I mean, I showed you a graphic of how much CO2 is coming out of Kilauea. Maybe I didn't show that, but in any case, there's a lot of CO2 coming out of volcanoes. So how do we know that we are the culprits and it isn't a natural phenomenon based on volcanic activity? Some would argue that, of course, it's volcanic activity. We have nothing to do with it. But it turns out that we do have something to do with it. This is the rise in the CO2. This is going back to, well, 1800 is where it started. That's the start of the Industrial Revolution, 1800s, late 1800s into the 1900s. And this is another graph of the carbon-13, heavy carbon. again, these heavy carbons and heavy oxygens are very useful in understanding climate change. Well, heavy carbon is created by cosmic radiation. The cosmic rays come down, they create heavy carbon, just like they create heavy oxygen. Then the dinosaurs die, they get buried, and they create oil way down, millions of years old. Oil is then being pumped up and burned. That oil doesn't have any heavy carbon in it because the half-life of heavy carbon is about 6,000 years. So a million-year-old oil that's being brought up has zero heavy carbon. And that's why the heavy carbon is dropping in the atmosphere at the same time that the carbon dioxide is increasing. And pretty much that's a smoking gun kind of evidence that we are the culprits. And this is what I just said. The time series of CO2 going back 400,000 years can be gotten from the ice cores, right? And so then we can just tack on what's been going on since the Industrial Revolution started. And basically that's it. 1950 is here. Current level is 421.47 parts per million. That's from Mauna Loa. And if you want, you can look. That was November 24th. You can look and see what it is now. We haven't seen anywhere near this much carbon for the last 650,000 years, probably 800,000 years. So this is definitely new and unusual. Now, is it new and unusual as far as the history of the Earth is concerned? No. We've had higher carbon levels, but it turns out that peak carbon levels, this is carbon going back in time, are related to mass extinctions. So it makes you wonder, do we really want to test this, see how much carbon we can get into the atmosphere, see if we can trigger a new mass extinction? We're already undergoing a mass extinction, according to scientists. But we might be triggering our own extinction by not paying attention. I kind of truncated this. This animation goes all the way back to the 1800s, but it takes too long. So I started it at 1970. So basically, this is from before when most of you have been born, right? And so at the bottom here is 1880. And this is 1900. So you can see that it was pretty stable. And then it was kind of a warm period, Dust Bowl time and stuff. And then we see global warming really ramping up. And the Clean Air Act was passed right around in here. So we have cleaned up our atmosphere in terms of particulate matter to a large extent in the United States. And that is part of the reason why we see a real acceleration in the warming, is that our atmosphere is cleaner, we get more solar radiation in, and we have more greenhouse gases. So our climate is shifting. And there's a way of looking at this too. If you subtract the mean, the average climate, and plot the standard deviation, the deviation from the mean, then you get this. And this is the decade from 1950 to 1960. And then as you go down, this last one is from 2011 to 2020. And what's happening here? Well, the mean is increasing. The global mean temperature is increasing. It's the same thing as I showed in the last animation. The mean is increasing, but there's an additional piece of information in this. This shows that you also still have extreme cold and you have extreme warm outside of the mean. You know, some days are really hot and some days are really cold. That's what's indicated by this, but the curve is flatter than it used to be. It used to be more peaked. And I can show that in the next diagram. It used to be a little bit sharper peak with, and so the new climate that we're seeing has more variation. We still have some very cold temperatures. In fact, there was a recent incident where one of the senators brought a snowball into the Senate. And I think he was trying to say, well, you know, global warming. But this is the problem. There are many more hot days and there are many more record hot days. That's absolutely true. So where is the heat going? And I'm almost through with the lecture today. It turns out most of the excess heat that we have been generating through the greenhouse gases is absorbed in the ocean. The ocean is an incredible heat sink because it has very, very large heat capacity. So the ocean has been taking more than 90% of the heat. And we see a little bit of temperature rise in the sea surface. And then the atmosphere is only 2.3% of the warming. So this is the ocean heat content. You can see it is increasing. And this is in joules, zetajoules. But that doesn't tell you a whole lot. But just the takeaway is that the ocean is warming. And next time, I'll talk a little bit about what the increase in the surface temperature, the sea surface temperature, is doing in terms of impacts. So next time I want to talk about some impacts, and then in the final lecture next week, I will talk about what we can do about it and why there's some reason for optimism. Yeah, but according to Sir David Attenborough, please make no mistake, climate change is the biggest threat to global security and that modern humans have ever faced. I agree with him. Are there any questions? Okay, I'll see you next week on Tuesday. And don't forget to check the homeworks. They're available on Laulima. And thank you.